Hi everyone, this is Larren, and today we're going over a related rates problem in which a conical tank with an upper radius of 4 meters and a height of 5 meters drains into a cylindrical tank with a radius of 4 meters and a height of 5 meters. If the water level in the conical tank drops at a rate of 0.5 meters per minute, we need to find at what rate the water level in the cylindrical tank will rise when the water level in the conical tank is 3 meters and 1 meter. So, our given information is the rate of change of height of the water in the conical tank. And we need to find the rate of change in the height of the water in the cylindrical tank when the height of the water in the conical tank is 3 meters and 1 meter. So our relationship formula for the volume of the cone is 1/3 pi r squared h. Now since we're going to be finding a rate of change, we're going to be using implicit differentiation. We don't want to have two variables to worry about. So we can find, using similar triangles, that the radius is equal to 4/5 the height, no matter what the height is. So substituting 4/5 h into our equation, we get the volume of the cone is equal to 1/3 pi times 4/5 h squared times h. Simplifying down, we get the volume of the cone is equal to 16/75 pi h cubed. Now, taking the derivative with respect to time, we get the rate of change in the volume for the conical tank is equal to 16/75 pi times 3 h squared times the rate of change of height in the conical tank. Substituting our known values and solving at a height of 3 meters for the water level in the conical tank, we get a negative change, or a negative volume rate of 9.05 cubic meters per minute. And then substituting our values in, or changing the height of the water to 1 meter, we get a change in volume, a rate of change of volume with respect to time of negative 1.01 cubic meters per minute. Now these are important because we're going to be inputting them into our equation to solve for the height of water for the cylindrical tank. So because the conical tank drains directly into the cylindrical tank, we know that the output, or rate of change in volume of our conical tank, is equal to, but opposite, the rate of change in volume for our cylindrical tank, as shown here. The fundamental relationship for the volume of a cylinder is pi r squared h, and we're given that the radius is 4 meters, and in this case it's a constant. So, because our radius is constant, we can just plug it into the equation. So we get the volume of the cylinder is equal to 16 meters squared times pi times h. Using implicit differentiation again, we find that the rate of change in the cylindrical tank with respect to time is equal to 16 meters squared times pi times the derivative of h with respect to time, because the 16 meters squared pi is a constant multiple. It gets to just go along for the ride. Now, substituting the rate of change of volume for the cylinder at 3 meters with respect to time, which is our negative 9.05 cubic meters per minute. We set that equal to our 16 meters squared pi times the derivative of the height with respect to time, and then divide by 16 meters squared pi to solve for our derivative of h with respect to time. This gives us the rate of change of height of water in the cylindrical tank with respect to time equal to negative 0.18 meters per minute when the height of the water in the conical tank is 3 meters. Substituting the height at 1 meter and our rate at 1 meter, which is negative 1.01 cubic meters per minute, we get a rate of change of height of water in the cylindrical tank of negative 0.02 meters per minute when the height of the water in the conical tank is 1 meter.